Okay, so here is a little brief review of momentum in case some of you guys have been slacking off for the past week or so. If you guys notice, here we have a new theme and hopefully it'll look prettier than usual. So let's begin. The three main topics I'm going to go over is the basics of momentum, impulse, and the conservation of momentum. After I go through each of these three topics, there is a series of practice examples that practice each of these three topics. So after I go through the content, I highly suggest you guys come with a piece of loose leaf or a scrap paper so that you can work along on the practice examples I have in this video. Alright, so I'm going to start with momentum being a vector quantity of motion. So vector meaning it has both magnitude and direction. And that direction follows the velocity direction. And where momentum is equal to mass times velocity, mass is the scalar. So thus momentum has to follow velocity, which is the vector quantity of this. And there is a linear relationship with mass and velocity towards momentum. So if you want to increase the momentum, then you got to increase both the mass and or the velocity. So increasing one or the other, or both, will result in an increase in the momentum. Now, the variable for momentum is lowercase p. So that means our equation here is lowercase p for momentum is equal to m times v. And the units for momentum is kilograms times meters per second, or kilograms meters per second. So momentum by itself is a pretty useless quantity, I must say, but what's more important here is how momentum changes, and so that's going to lead into the next idea of impulse. And so impulse here is the force multiplied by the time duration of that force. So impulse is given by the variable capital J. So capital J is equal to the force F multiplied by the time t. So J is equal to F times t. Now impulse is also known as the change in momentum. So the symbol for change is delta, and momentum is still our variable lowercase p, so delta p. And how do we change an object's momentum? The only way we could change an object's momentum is typically by changing its velocity. So delta p here is equal to the mass times the change in velocity, which is also equal to Vf minus Vi. So if you're given two velocities, you take the final minus the initial and you get the delta V. Now if you take a look here, I mentioned before that impulse is equal to the change in momentum. So that means, I'm going to write this elsewhere, J is equal to delta P. But wait, delta P is also equal to m delta V. And if you look on the other side, J is also equal to F times T. So that means this entire chain here is all equivalent to each other. And when you're solving impulse problems, you're probably going to take 2 out of these 4 and solve for what you're missing. So even though you have 4 different types of quantities here that are all equal to each other, you're most likely going to only use 2 of these when you're solving problems related to impulse. And just a reminder, J is equal to impulse, F is force, T is time, delta is the change, so delta P is the change in momentum, M is equal to mass, and then there's delta V, which is change in velocity. Okay, and the unit, oh I forgot that, the unit for impulse is newtons dot seconds, or kilograms meters per second, which is the same as for the change in momentum. Okay. Now we're going to get into this idea of conservation of momentum. So when you apply an impulse, this force over a time duration, to change an object's momentum, that momentum does not disappear. So where does it go? It transfers into another object. But it does not transfer into any old object. It has to transfer into an object it collided with. So if you have an object here moving this way and it collides with another object, kapow, then that momentum transfers over. So when objects collide, momentum is transferred. So by transferring momentum between objects, the momentum of the entire system, however many objects are involved, is then conserved. So like conservation of energy or mass or matter, where they cannot be created nor destroyed. Similar with momentum, it cannot be created nor destroyed. It comes from another object. And so typically, when objects collide, you're going to have changing momentums of individual objects, but the total momentum of the system does not change. So the total momentum before the incident is equal to the total momentum after. And so this typically deals with problems where you have collisions, car accidents, explosions, or something where a force is exerted to change a momentum. So you gotta, when you're approaching these problems, you gotta divide them up into before and after and list what is happening there. And let's take a look at some of these examples. Okay, so we're looking for speed of a 1,000 kilogram car that has a momentum of 20,000 kilogram meters per second going east. Alright, we're looking for V. Our mass is 1,000 kilograms. Momentum is 20,000 kilograms meters per second. So P equals M times V, 20,000 equals 1,000 kilograms times V divided, and then you should get over here, my brain is not working for a moment. 20 meters per second. So 20 times 1,000, okay, gets us 20,000 kilograms meters per second. Okay. Next problem. 0.06 kilogram ball traveling 60 meters per second hits a concrete wall. What speed must a 0.01 kilogram bullet have in order to hit the wall with the same magnitude of momentum as the ball? So the momentum of the ball has to equal momentum of the bullet. Alright. So they're both equal to M times V. So let's start with the ball. Kilograms times 60 meters per second has to equal the mass, the bullet, times the speed that we're looking for so that they equal each other. Alright, you solve. I'm just going to continue this over here, and you get 3.6 is equal to 0.01 V. Divide 0.01 on both sides, and you get 360 meters per second as your answer. That's fast. Okay, now we're on to impulse. So here we're given a 3 kilogram object with an impulse of 15 newtons dot seconds. And we're looking for the magnitude of the change in momentum. Oh, that is not a pretty color. Well, that's not pretty either. Oh, wow. Okay, so we're looking for the change in momentum, so that variable is delta P. Change meaning delta, P meaning momentum, so delta P. And if we look at our four-way relation here, J is equal to F times T, which is equal to M delta V, which is equal to delta P. Now if you notice here, these two are equal to each other. So that means J equals delta P, which has to equal 15. Same value, just different units. Now here we got a bicycle and its rider with combined mass 80 kilograms with a speed of 6 meters per second, magnitude of the average force needed to bring the bicycle and its rider to a stop. So that means our 6 meters per second is our initial velocity and our final velocity is 0, and our time interval here in 4 seconds. So that means we're going to use, if you look at our four-way relation, we're going to use F times T is equal to M delta V. Now look here, we only need the magnitude so we could forget the sign, so we're going to go proceed on anyway. F times T is 4 seconds equals 80 kilograms times delta V, 0 meters per second minus 6 meters per second. Okay, 4F is equal to negative 480. I believe so. So F is then equal to negative 120 newtons. Negative meaning it's acting in the opposite direction, but we're only looking for the magnitude, so we just need this. Forget the sign. Forget the direction, we just need magnitude. There we go. Alright, 2 kilogram body. Initially traveling with velocity of 40 meters per second. Due east. If a constant force of 10 newtons due east is applied to the body for 5 seconds. What is the VF? Ooh, if it's in the same direction, that means we're going to go faster. Just so you know. So VF we're looking for minus our VF 40 meters per second, 50 over here, 2VF minus 80, bring 80 to the other side, 130 equals 2VF. That means VF is equal to 65 meters per second. Did we go faster? Yes, we did. Alright, now we're on to the tricky problems, conservation of momentum. So we're going to start here with a truck moving with velocity of 10 meters per second, hitting a parked car. How unfortunate. Okay. Let me pick a different color. Alright, so I'm going to call this MT for the truck. And then we have the parked car, MC. You can use different notation, A, B, 1 or 2. I like to use the letters. Okay, so the truck was moving 10 meters per second. So the initial velocity of the truck was 10 meters per second. Parked car, what does that mean? Initial velocity is 0 for the car. The impact causes the 1,000 kilogram car to be set in motion at 15 meters per second. That means the final velocity after the collision for the car is going to be 15 meters per second, and we got to figure out the velocity of the truck. So that is VTF. Okay. What equation are we going to use now? So that brings out that handy dandy equation. Okay. Now if you notice here, the initial velocity of the car is 0. So that becomes 0 on that side. Now let's continue plugging things in. Okay. Solve. Bring it to the other side. You get 15,000 equals 3,000 VTF. Divide by 3,000. And you should get that VTF is equal to 5 meters per second. Okay, that makes sense. And it's positive, meaning they're both moving in the same direction afterwards. So he rear-ended that parked car and they both moved together. Alright, so this time we have a cannon at rest with a cannonball inside the cannon. Then it exploded and both objects move in opposite directions. So this is an explosion type of problem, meaning they both start at rest and then they explode, giving a velocity. So let's start. M1 for the ball is 8 kilograms. M2 for the cannon is 1,000. Both are at rest. Initially, we know that the momentum of the ball is this value. You got to figure out the velocity of the cannon. Alright. Okay. Yeah, this part can get very tedious, guys. Alright. So, initially they're both at 0, so this entire left side is 0. We already know the momentum, so we don't need to do that MV. Okay, the M2 for the cannon is 1,000. Oh my goodness gracious. Solve for V2F. And you get negative 2.4 meters per second. What does the negative mean? Opposite direction. So when the cannon fires, both the ball and the cannon move away from each other in opposite directions. Alright, and finally, my favorite type of problem. When you have objects collide head-on, they stick together, and they still move. That's a very brutal collision. Okay. So let's start with the truck. 3,000 kilograms. Then we got the mass of the car being 1,000 kilograms. The initial velocity of the truck is 5 kilometers per hour. It's okay, we don't need to do any conversions here. Alright, now the tricky part here is the initial velocity of the car. I'm going to highlight it here. It's moving leftward. So that means it's moving in the opposite direction, so that means we got to make it negative 10 kilometers per hour. Now the both vehicles stick together. That means their masses add up. You add their masses on the after side, and they move with the same velocity after the collision. So when you set this up, we gotta make sure we understand that when they stick together, you add their masses together, so that you could show and indicate that they're gonna share the same velocity. Next, you're just gonna sub it in. I'm just gonna write the rest of this underneath it. So 1,000 kilograms plus 3,000 kilograms times VF. Alright, next step. Different color. 3,000 times 5. 15,000 minus 10 times 10 times 1,000 is minus 10,000 equals 1,000 plus 3,000, that's 4,000 VF. 15,000 minus 10,000 gets you 5,000 equals 400 4,000 VF. 5,000 divided by 4,000, then you get that VF is finally equal to 1.25 not meters, 1.25 kilometers per hour. Now, does this make sense physically to you guys? When two objects stick together and they move, will it be slower or faster than before? Because they're going to add masses together, they're likely going to move with a slower speed. So physically, this does make sense. Our numbers check out. Alright, so that's the end of this video. And hopefully this will help. Good luck on the quiz. You're going to need it.